Okay, great. We're going to continue talking about cryptography today. And actually, in the last session, we had an attempt at obtaining RSA, but it failed miserably. So we're going to look at that again, and we're going to see how we can fix it. So remember, the idea was that we're going to have two different keys. So we have a public key, or let's call it an encryption key, E. And then we have another key for decryption. And the encryption key is public, but there is also a private or secret or decryption key, D, and this is supposed to be private. And we had this idea that we want both encryption and decryption to be really simple. So I said that if I have a message M and I want to encrypt it using the key E, I want this to just be M to the power of E, right? And I wanted decryption to be very similar. So if I'm decrypting using D, some encrypted message M bar, I want this to just be M bar to the power of T. And of course, we said that we have a prime number and we're doing all of these calculations modulo that prime number. So this was supposed to be modulo P, and this was also supposed to be modulo P. Now, we wanted to make sure that whenever we encrypt and decrypt the message, we get the same message back. So we wanted to have this property for every message M. And this is like for every M that is relatively prime to P, right? So other than 0, basically. All of my numbers are modulo P. So my message is not 0. So whenever I write for every M, you can just imagine that it's not 0. I want to say that if I encrypt my message M using my encryption key, and then I decrypt it using my decryption key, that gives me the same message M back. Okay, and we just wrote this. It means that M to the power of ED is equal to M. And then we were looking for sufficient conditions on E and D to ensure that we have this, right? And the way we got these sufficient conditions was that we said, well, it's sufficient if I have M to the power of ED minus 1 is equal to 1. And of course, all of these things are mod P. Right? But in order to have this one, in order to have M to the power of ED minus 1 equal to 1, it is sufficient if this power ED minus 1 is a multiple of P minus 1. Because I know that M to the power of P minus 1 is 1. Okay, again, this is not 0. So it is enough to have P minus 1 divides ED minus 1. So look, I'm not saying it's necessary. I'm only saying this is sufficient for that one. Right? So it might be that you find some E and D that satisfy this one, but not this one. Right? So what I'm claiming here is that if P minus 1 divides ED minus 1, then I have this condition. And if I have this condition, then I can multiply both sides by M, and I will have this. Okay. But then this means that ED minus 1 is 0 modulo P minus 1, which means that E is the inverse of D, because ED would be 1 modulo P minus 1. Okay. So this gave us a way of generating our keys, a way of generating the numbers E and D. And the idea was that I'll just pick a D at random, and then I'll take its inverse modulo P minus 1, and I call that E. Right? And then all of these things will work out. Because E is the inverse of D, I have this one, and because of this, I have this one, and so on. And I get to the final desired property that M to the power of ED, which is the decryption of encryption of N, is the same as it. Okay. And we also talked about basically how you can generate this, right? So you pick a large prime number, and then you pick a D at random. Now you might be unlucky, and maybe the GCD of D and P minus 1 is not 1. Maybe D doesn't have an inverse modulo P minus 1. You just throw out that D and pick another D. Right? So you do this randomly until you generate a pair of E and D. And then the idea was that you keep D to yourself because this is your secret key. This is the key that you're using for decryption. And you announce E to everyone else. So whoever wants to send you a message, they just need to know E. And they can, E is public, everyone knows it. So they can just raise their message to the power of this public key and send you that. Okay. But of course, at the end of the previous session, we saw the problem with this. And the problem is that anyone who knows the public key can find the private key. Right. So if this is my key generation algorithm, written from the bottom up, then what happens in this case is that everyone knows P. Because of course they have to know P, because if I don't give them P, they can't do encryption. Right? My calculations are modulo P, so whoever is doing encryption and wants to send me messages has to find this M to the power of E modulo P. So I have to make P public. Right? They also know E for the same reason, because they need it in order to do encryption, in order to send me a message. So since everyone knows P and E, everyone can find P minus 1, just subtract 1 from P. And then we've seen the algorithm for computing modular multiplicative inverse, which is just the Euclidean algorithm for GCD, basically. Right? So anyone who knows E can find D. So everyone knows P and E and can compute D, which is just the inverse of E modulo P minus 1. Okay. Now, we want to fix this. How can we fix it? So the problem here is the use of this prime number. Because I'm using a prime number P, I can do all of these things. Suppose that instead of using a prime number, I was using a non-prime number N, a composite number N. What would happen in that case? So just imagine that all of these calculations are modulo N. Well, some of these things will not make sense, right? So for example, this part, this doesn't make sense anymore, because we don't have Fermat's little theorem in the general case for all natural numbers. We have it only for prime numbers. But let's look at it from the point of view of an attacker. An attacker who knows, now let's say my modulus N, no longer calling it P, and also knows this encryption key. So what would my decryption key look like? My decryption key would be the inverse of my encryption key modulo what? It's no longer P minus 1 here, right? It's going to be modulo phi of N, where phi is the Euler-Stoichern function. Okay. So intuitively, what I want to do is I want to choose a number N such that it's hard for an attacker to find phi of N. Okay. But does that make sense to you? Like, I'm giving you these numbers. So here I'm giving you P. So phi of P, since P is prime, is just P minus 1. So anyone who knows P can compute P minus 1. But if I give you any natural number N, we've already seen a formula for phi of N, right? You just take the prime factorization, and after you have the prime factorization, there is a simple formula. It's just N times 1 minus 1 over Pi. For every I, just multiply it, right? Now, but the interesting thing is that whenever in cryptography we're talking about a modulus, we're not really talking about a small number. Our numbers are huge. So remember, even when we were doing Diffie-Hellman and I was talking about prime numbers, I said we pick a prime number that is thousands of digits long. Okay. So if you have a number that is thousands of digits long, or maybe even millions of digits long, do you have a good algorithm to somehow find its prime factorization? No. If I give you a number that is a million digits long, how would you factorize it? So let's just talk about factorization before coming back and trying to fix this mess here. So this is the factorization problem. In the input, I'm going to be given a number n. Or actually, let me write it like this. I'm going to say a number big N with small n digits. Okay, so small n is log of big N. Okay. Because I want to talk about the size of my input, and the size of my input is the number of digits in my number. So I want n to be the number of digits. And let's say that I'm also guaranteeing you that this number is composite. So n is not prime. Okay. And all I want you to do is to factorize n, which means I don't want the prime factorization. I just want you to give me two numbers that when I multiply them together, they will give me n. Okay. So I just want a factorization. Let's call it a and b, such that a times b is n. Okay. Now, let's try to come up with some algorithms just to see like how this problem looks like. The simplest thing I can do is to just try every possible factor, right? So I can just have a for loop that starts from 1, but not from 1, from 2, and then just checks, is n a multiple of 2? Is n a multiple of 3? Is n a multiple of 4? And so on, and keeps going until it finds a factor, right? So I can have such an algorithm. This is algorithm 1. I'm just going to write it as pseudocode. So I just say for a from 2 to big N. Actually, this is more C++ than pseudocode. Anyway, if n is a multiple of a, then just return a and n over a as your factorization. Okay. And of course, this will work because I'm saying that I'm guaranteeing the input number n is composite. So at some point, I'm going to get to one of its factors. And actually, I'm going to get to its absolutely smallest factor. And when I see the smallest factor a, I'm going to just return a and n over a. Okay. Now, analyzing runtimes of algorithms is not for this course, it's for 3711. But let's just analyze a very simple thing here. How many different values will I try for a? Okay. So you can say that, well, at most n minus 1 values. Actually, it doesn't have to go all the way to n itself either, right? I can say a less than f. So I'm trying all the values from 2 to n minus 1. So you can say at most n minus 2 values, right? And this part is super fast, right? So I don't really care how much time this one takes. This one takes very little time. So the whole runtime is something like n minus 2 iterations, right? But it's actually better than that, if you think about it. Yes. So the idea is this. If a times b is n, then one of them has to be less than or equal to square root of n, right? I cannot have both a and b being greater than square root of n. So if A times B is equal to N and A is less than or equal to B, then A is less than or equal to square root of N. Which means that in this algorithm, even though I have written my algorithm like this for loop is not going to go after square root of N, because it's going to find the smallest factor of N, and the smallest divisor of N other than 1 is definitely less than or equal to square root of N. Okay, great. But this immediately gives me an algorithm for checking whether a number is prime. Right. So maybe I'll just go here. This is algorithm 2, checking whether a number is prime. So because of this simple lemma that I have here, if I'm given a number n and I want to see whether it's prime, I just have to check if it has a factor between 2 and square root n. Right? So I can just have something like this. I can say for a from 2 to square root n, sorry, this was big N. This one is also big N. Okay, so I say for every a from 2 to a square root n, if n is a multiple of a, then you just return false, saying that it's not prime because it's a multiple of a. Otherwise, if you didn't return false anywhere in this for loop, when the for loop is over, you return true, it's a prime number. Right. Great. But again, the important thing is that if you look at the runtime of this algorithm, if you look at how many steps it takes square root of big N steps, right? So big N is my whole number. It's not the number of digits. So if I have a number that is hundreds of thousands of digits or millions of digits or even thousands of digits, this algorithm is not really going to terminate in our lifetime. It's not going to give you a factorization. And of course, this kind of factorization is much easier than prime factorization, right? Because if I want to have the entire prime factorization of a number, I would have to find all the prime factors. In this case, I'm only finding the smallest one, right? Yeah, you can also prove that the a that I find in this case is prime. Right? So if my number n is huge, if it's thousands of digits long, this algorithm doesn't work. But what's more interesting, and somehow also depressing because we cannot prove it, is that no one knows a good algorithm. So integer factorization is a hard problem, not in the sense that we can prove there is no fast algorithm for it, but in the sense that people have tried for almost 100 years. No one has a fast algorithm for this. Okay. So this is very similar to the case that we had for discrete logarithm. So integer factorization is hard. Now, you might think this is bad news, and well, to some extent, you're right. But it's good news when we go back to cryptography, because whenever we have a problem that is hard, whenever we have a problem that is not solved, I can use that as the basis for my encryption. I can say, well, I design an encryption and decryption scheme such that if anyone can somehow find my decryption key or can somehow decrypt my messages, that means that they have solved one of these unsolved problems. So that's what I want to do here. And actually, this is finally the RSA algorithm. So, and RSA stands for the names of the people who designed the algorithm. So I think it's Rivest, Shamir, and Adelman. I cannot spell those names. And so here's the idea. I want to do the same encryption and decryption as my failed scheme. I want to just raise my message to the power of my key. But now, instead of doing the calculations modulo a prime number, I'm going to take two prime numbers, multiply them together, and do all of my calculations modulo this product. Okay. So this is my key generation. I basically say this. I say, first, pick two large prime numbers, P and Q. And you're going to keep these numbers P and Q to yourself. They're going to be secrets. Okay. And then let's calculate their product. So let N be P times Q. And we're going to announce N, and we're going to do all of our calculations modulo N. I just realized I'm too lazy for writing big N, so I'm just going to write small. Okay. So all calculations will be modulo N. Okay. Now, I want to have the same encryption and decryption as before. So before coming back to the rest of my key generation, let's go here and let's say this is my encryption. I want to say that if you're encrypting some message M using the public key or encryption key E, this is just going to be M to the power of E. But now it's modulo N, and my N is no longer a prime number. Okay. And if I want to decrypt, so if I want to decrypt some received message M bar, so some encrypted message M bar using my private key D, this is also just raising the message to the power of the key module. And why am I doing this? I mean, of course, it's simple, but it's also quite easy to compute because I know how to compute powers really fast. Okay. But now I need to have that property that I'm always talking about, that if I encrypt the message and then decrypt it, I want to get the same message back, right? So this is what I want. I want to say that for every message M, and now here I'm going to add an assumption. I'm going to say my message is relatively prime to my modulus N. Now, why am I doing this? Well, because the idea is that I'm choosing two prime numbers, P and Q. I'm keeping P and Q to myself. So I'm not announcing P and Q. I'm only announcing N. So everyone on the network, everyone who's in this system wants to send me messages or is an eavesdropper or whatever knows N, right? And my security is going to depend on the fact that they cannot factorize N. Okay, so if I send a message that is not relatively prime to N, they can just take the GCD of my message and N, and they can factorize N. Right? But now in practice, it's very rare. Like if you have numbers P and Q that are thousands of digits long, it's very rare that your message actually doesn't have GCD of 1 with N. Right? That's not going to be a likely thing. So it will not really happen. But mathematically, we have to say for every message that is relatively prime to N, I want to say that if I encrypt this message using my encryption key, and then I decrypt it using my decryption key, then this is the same message. Okay. Now, I still haven't told you how my key generation works because I'm going to build it based on this. So again, the decryption of encryption of M is just M to the power of ED, and I want this to be M. And remember, all of my calculations are modulo N. Okay. So m to the power of ed is equal to m. In order to have this, it's sufficient to have m to the power of ed minus 1 is 1 modulo n. Okay, and what do I need for this? Like, what would be sufficient for this, actually? So if ed minus 1 is a multiple of phi of n, right? Because we've seen Euler's theorem, we've seen that m to the power of phi of n is 1 modulo n, right? So if this power here is a multiple of phi of n, then I have what I want. But what is phi of n? Phi of n is just p minus 1 times q minus 1, right? So n was p times q, so just use the formula. Phi of n is p minus 1 times q minus 1. Great. So I want phi of n to divide ed minus 1, and then the rest is pretty much similar to the previous case, right? So I want ed minus 1 to be equal to 0 modulo phi of n, which means that ed is 1 modulo phi of n, which means that I want E to be the inverse modulo phi of n. Okay. Great. So this gives me a way of doing my key generation. So my step 3 is that I just pick some number d and let E be the inverse of d. Okay, but this is the inverse modulo phi of n. Okay, and well, I can easily calculate phi of n because I know p and q. And phi of n is just p minus 1 times q. Okay, and then the rest of it is very simple, right? So I just announce n and e. So I announce my modulus and I announce my public key. And anyone who wants to send me a message knows that they have to raise their message to the power of this encryption key E and take its remainder modulo n, and that's what they send. And when I want to decrypt it, I just raise it to the power of t. Okay, so this is pretty much the same algorithm, except that instead of doing it modulo a prime number, I'm doing every calculation modulo n, which is a product of 2 prime numbers. Okay. Why doesn't the same attack as before work here? Because suppose you're an attacker, and suppose that you know n and you know e, right? What do you know about d? What do you know about the decryption key? You know that it's going to be the inverse of e, but that inverse is modulo phi of n. But you cannot calculate phi of n as an attacker. Why can't you calculate phi of n? Because, well, phi of n is p minus 1 times q minus 1. And we said integer factorization is hard. So you don't know p and q, you don't know p minus 1 and q minus 1. You cannot find phi of n, you cannot find the inverse. That's the intuition. But again, of course, this doesn't have a proof. It's just an assumption. It's the RSA assumption. The RSA assumption is that given n and e, it is hard to find d. Or given n and e, it is hard to decrypt any message, actually. Because I don't know, maybe someone can somehow decrypt a message without actually knowing d. So that's again the RSA assumption, and it's an assumption in the sense that we don't have a proof. It's just that many people have tried over many decades to do this, and they couldn't do it. Okay, great. But just a small footnote here. I don't really need ed minus 1 to be a multiple of phi of n. I can do a little bit better than this. Okay, so let's just go back to this analysis here and let's see what else I can do. I mean, it's for you to decide if this is really better or not, but it's a fun thing to talk about. So here's what I want. Erase the parts I don't want to use. Okay, remember that N is P times Q. I want the decryption of the encryption of every message to be that message itself, which means that I want M to the power of ED to be equal to M. And I said that in order to have this, it is sufficient to have that M to the power of ED minus 1 is equal to 1 modulo N. And again, this N was P times Q. But I can just apply the Chinese remainder theorem here. So I have a number, M to the power of ED minus 1. I want this number to have a remainder of 1 when divided by N. It's enough if this number has a remainder of 1 when divided by P and a remainder of 1 when divided by Q. So basically what I'm saying here is that if I have M to the power of ED minus 1 is 1 modulo P. And if it's also 1 modulo Q, then this is sufficient to have M to the power of ED minus 1 is 1 modulo N. This is just by the Chinese remainder theorem. Because again, N is P times Q. So if you consider this as like two equations, X is equal to 1 modulo P, X is equal to 1 modulo Q, it's going to have exactly one solution modulo P times Q. Okay. So it's enough for me to have these two things, but now I can use the same analysis that I had for my first failed algorithm. So I want M to the power of ED minus 1 to be 1 modulo P. So it's enough if ED minus 1 is a multiple of P minus 1, right? So if I have that P minus 1 divides ED minus 1, then I will have this one. My arrows are getting out of control. And similarly, if I have that Q minus 1 divides ED minus 1, then I will have this one. So it's enough for me to have these two properties. P minus 1 divides ED minus 1 and Q minus 1 divides ED minus 1. But well, I have two numbers. I want each of these numbers to divide this other number ED minus 1. This happens when their lowest common multiple divides it, right? So what I need here is that the lowest common multiple of P minus 1 and Q minus 1 divides ED minus 1. Okay. Now, why is this better? Because before I had this, I had phi of n divides ED minus 1, and phi of n is just the product of P minus 1 and Q minus 1. But now I'm saying instead of taking the product of P minus 1 and Q minus 1, it's enough to just take their LCM, which is potentially smaller than the product, right? So it's enough if I have this, if I have that the LCM of P minus 1 and Q minus 1 divides ED minus 1, let me give that LCM a name. I'm going to call it L. So let's say L is the LCM of P minus 1 and Q minus 1. And all I need now is that E is D inverse modulo L. Again, all of these steps are the same as before. So ED is 1 modulo L, so E is D inverse modulo. Okay, so I can change my key generation algorithm a little bit by saying that instead of doing this part modulo phi of n, find this inverse modulo the lowest common multiple of P minus 1 and Q minus 1. And everything else will still go through. Okay. Great. And again, remember the RSA assumption, and I call it an assumption because there is no proof, is that if you know the encryption key E and the modulus N, and let's say you also know a bunch of encrypted messages. So suppose that you're someone who's listening on the network. Let's say I'm the person who owns this private key, and a lot of different people are sending me messages. So let's say you know E, you know N, and you know the encryption of many messages. Assuming all of these, you cannot decrypt any message. Of course, I can add unless you know the decryption key D, or unless you know P and Q. Okay, so if you know these things, if you can observe everything that is public on the network, but you don't know P and Q, unless you know PQD. So if you don't know these values of P and Q and D, no matter what you're seeing on the network, you will not be able to decrypt any message. That's the RSA assumption. And by the way, I'm saying unless you know P, Q, and D, but if you know one of them, you know all three of them. Right? Well, no, if you know P, you definitely know Q and vice versa. And if you know P and Q, then you know D. If you just know D, can you find P and Q? I don't know. But that's nonsensical anyway, because if you know D, you can decrypt everything. Right. Okay. But now, one important point is that you should not leave this session and go and implement your own RSA in Python, because that will not work. Look, when we're talking about hard problems, we're talking about hardness in general. It's like when I say factorization is hard, it means that if I have no control over this number n, if I know no particular property of this number n can be anything, then I don't have an algorithm for it. Right? But there can be algorithms for special cases of this. So for example, imagine that this number n is a power of 2. Of course you have an algorithm for that, right? You just, if n happens to be a power of 2, you just factorize it. Or in this case, when you are taking p times q, if one of these numbers is really small, if p is, let's say, less than 100, right? You can just try all the values up until 100, and that's an algorithm that gives you p. Another case where it's really bad is if p and q are really close together, which means that both of them are close to square root of n. You can find square root of n, and then you can start searching from there. So you start at the end, at square root of n going back, right? And if p is close to square root of n, you will find it. But I mean, these are the easiest special cases. There are actually many special cases. Like if p is close to a power of 2, there are algorithms that will find this factorization here. So it's really important for you to understand that breaking RSA is hard in the general case, but there are many special cases that are solved. So unless you know all of those special cases, you should not implement your own RSA, because it might be that your own RSA just gives you outputs, generates keys that are part of those special cases, and then someone can decrypt it. Okay, so there are standard libraries for this. There are researchers whose work is to just keep track of all the special cases that are solved and just use those. Okay, great. So what we have so far is that, again, we have this network. So I have one person on one side and many other people on the other side. And the idea is that this person, let's call him Bob, now has several things. He knows n, he knows n is not. So he knows p, he knows q, he knows d. Of course, he also knows N and E. And then he has announced N and E to everyone. And then we have a bunch of people who want to send messages to him. They use E to encrypt, and he uses D to decrypt. But in practice, the way this works is that each person has their own encryption and decryption key, right? So if Alice wants to send a message to Bob, Alice would encrypt it using Bob's public key. So if Alice wants to send a message to Bob, Alice will use the N and E that Bob has announced. But then if Bob wants to send a message to Alice, there's going to be a different N and E, which was generated by Alice and announced to everyone. And Bob is going to use that to encrypt the message for Alice, and so on. Great. And again, if we have an eavesdropper in between, that doesn't really matter to us. This person can see everything. We don't care. As long as the RSA assumption holds, it's going to be secure. But now let's give Eve more power. So until now, this was just an eavesdropper. So she was just listening in on the communications, maybe spying on people, but not really changing anything. But now, suppose that we have someone who's trying to also fake messages. Okay. So now, the way I want you to think of this adversary is, again, this is your internet service provider. So it's not just that they can see the messages you send, they can also change them. Right? So now we have this situation. Let's say I have Alice and Bob again. And let's give our adversary a new name because they're now a different adversary. What's a good name for someone who changes things? I don't know. Okay, let's call it Dave. Okay. So the problem here is that Alice wants to send a message to Bob, Bob wants to send messages to Alice, and so on. But Dave can not only intercept the messages, he can also decide, well, I'm not going to deliver this particular message. Or he can decide that I'm going to fake it and deliver some other message. This is actually something that you can do over the TCP/IP protocols of the internet, for example. You can send a message to someone claiming that it comes from a particular IP address, but they don't know if it's really from that IP address or not. Okay. So let's see what happens in this case. So let's say that Bob has a private key or decryption key. Let's call this D of Bob. And he also has an encryption key, E of Bob, which is public. There is a modulus, N of Bob. And then Alice has the same thing. So she has her decryption key, D of Alice, but there is also E of Alice and N of Alice. Okay. Now let's say that Alice wants to send two different messages to Bob. So let's say there is a message M1. I'm running out of space, so I'm just going to go out. So M1 and M2, and Alice wants to send these messages to Bob. Now, how does this work? Well, Alice wants to send message 1, so she's going to encrypt message 1 and send this. I'm not going to write the key here. You just know that it's using the encryption key of Bob. And she wants to send message 2 as well, so she's going to encrypt this message 2 as well. Now, Dave is going to intercept both of these messages. So these messages may or may not be delivered to Bob. Dave makes that decision. But here's what's going to happen here. What is the encryption of M1 using the encryption key of Bob? It's just M1 to the power of this encryption key of Bob. Of course, modulo N of Bob, right? Now I can look at the encryption of M2. And this is M2 to the power of the same encryption key E, modulo the same thing. Okay. So what Dave can do is he can take these two things and multiply them together, right? So I'm not going to write E sub Bob anymore. I'm just going to write E, but I mean E of Bob, right? So he knows M1 to the power of E. He knows M2 to the power of E. He can multiply them together, and this gives M1 times M2 to the power of E. Okay? And again, this is all modulo N of Bob. This is like E of Bob. Okay. So you're sending two different messages, but this adversary in the middle can intercept them, and he can just create a new message that you didn't expect, and he can send this. Okay. But is this a problem? Not necessarily, because I mean, he could send this message anyway. He could encrypt anything, right? So you might think that this is not a problem, but it can be a problem, right? Because maybe Alice and Bob have some protocol about their messages, about M1 and M2, right? So in this case, Bob is getting the encryption of M1 times M2 without even having to find M1 and M2 themselves, right? So Bob doesn't know M1, Bob doesn't know M2, but he could somehow compute the encryption of these messages. And he can now send a fake message to Bob. And this fake message is actually dependent on the messages of Alice. So this Dave is going to be able to really change some things. But there is a bigger problem. And the bigger problem is that suppose Alice hasn't sent a particular message. There is, let's say, another message M3. And this is just a fake message that Dave wants to send, right? So Dave can just send a message like this, right? Sending the encryption of M3. And he can pretend like this message came from Alice, right? So if you've ever got a spam email that was from a university email address, and sometimes, especially if you're using Gmail, it tells you this message does not have the correct signatures. That's what's happening there. So with the traditional email protocols, you can do this easily. There are actually websites that let you just do this. You can send an email from any email address. There's no control over it. Because the way an email works is that it's just a message. And as part of the message, it contains the address of the person who's sending this message. So I can just fake it. I can just put your address and send an email to someone from your email address. Okay. Another reason why you should never trust emails that you get. Okay. Yeah, and if you want to try this, please don't try it with my email address. I mean, there are so many different things. You can just Google for like fake mailers, and you can send an email address from, I don't know, president@whitehouse.gov or something. But don't use my email address. Okay. So we want the way for Bob to be sure that when he receives a message, that message actually came from Alice. And this is what we call a digital signature. Okay. So when we're talking about digital signatures, the problem is not really whether the message is private or not, whether someone can read it or not. So imagine for a second that you don't care if someone reads your emails. And imagine that you just care whether a particular email is really from the person that it's claiming to be from. Okay. So we want to have something like a real world signature that authenticates the message, that says that this message really came from the person that it's claiming. Okay, so what are the properties that I want for this signature? I want to have basically two functions again. So let's say M is my message. Let M be a message. I want to have a function for signing M. Okay, so I want to have a function sign that takes a message. And again, when I say a message, it can be a number, it can be a sequence of bits. These are the same thing. And gives me a signature on this message. So sign is a function from messages to messages. Okay. And then I want to also have a function for verifying signatures. Okay, so I want to have a function verify, which basically takes a message and a signature on that message and just gives me true or false or 0 or 1. Is this a valid signature or is it not a valid signature? Okay. Now, what are the properties that I want to have here? So imagine that Alice is the one who wants to send a message to Bob, and Bob is the one who wants to verify that the message came from Alice. So when I'm doing signing, I want to make sure that only Alice can sign. Right? So I want this. I want to say only Alice can sign. And what I mean by this is that no one else should be able to fake Alice's signature, right? Because if someone else can sign, what's the point of the signature in the first place? So only Alice can sign, but I want everyone to be able to verify. So given a message and a signature, M and S, everyone can verify whether S is a valid signature of Alice on M. S is Alice's signature on M. So I want to have these two properties. I want to make sure that only one person can sign, but everyone can verify. But this has a lot of similarity with what we've had up here when we were doing encryption and decryption, right? The idea here was that everyone can encrypt because everyone knows the encryption key. The encryption key is public. But only one person can decrypt because in order to decrypt, you need the decryption key. And to use the decryption key, I'm assuming that there's only one person who knows this decryption key. So there's only one person who can decrypt, right? So the properties that I need for digital signatures are actually pretty much the same as the properties that I needed for my encryption and decryption. It's just that only Alice can sign. This is basically saying that signing should be similar to decryption. It should be something that only one person can do. And I want everyone to be able to verify. So that means that verification should be similar to encryption. It should be something that everyone can do. Okay. So this is the intuition I have, that verification is very similar to encryption because everyone can do it. And signing is very similar to decryption because only Alice can do it. Okay, so I can say whenever you want to sign, you have to do it using a secret key. And I'm going to use D again, but this is not really a key used for decryption. It's actually a key used for signing, right? And when you verify, you're going to verify using the public key. And actually, I'm just going to say that the sign function is exactly the same as the decryption function, and the verify function is exactly the same as encryption function. So this is how I define RSA signatures. So I say RSA signature is like this. If I want to sign a message M using a secret key D, this is just going to be M to the power of D modulo I. And if I want to verify a message M and some signature S using E, using a public key E. What am I going to do? I'm just going to raise S to the power of E, right? So it's like encrypting S. Okay, and then I check, is this the same as M? Of course, this calculation is also modulo N. And if it passes the check, it's a valid signature. If it doesn't pass the check, it's not a valid signature. Okay. So basically here, my signature is my message to the power of D, and my message is my signature to the power of E. And everything works out for the same reason as RSA working out. Great. So now we go back here and we say, well, Alice, if you want to send a message to Bob, instead of encryption, let's forget about encryption now, and let's just use signatures. So let's say I don't care if Dave can read the message, but when Alice wants to send a message M1 to Bob, she's going to send M1 itself, so leaking the message. And she's also going to sign M1 using her own private key D of Alice and send that. Okay. And similarly, when she wants to send M2, she sends M2 and she sends her signature on M2 using D of Alice, so many things of M2. Okay. So now when Bob receives these messages, he receives M1. He's not sure that M1 is from Alice, but then he receives the signature. So he can just verify the signature. Takes the signature, raises it to the power of E of Alice, and if it's the same as the message, he knows that it came from Alice. Now, if Dave wants to send another message M3, he cannot do it. Right? Because, again, if you are able to create a signature on M3, since signing was the same as decryption, and since we have the RSA assumption which says no one else can decrypt, no one else can sign either. So Dave should not be able to sign M3. But now suddenly this one becomes a big problem. Right? Because previously I was doing encryption, but now I'm doing signing. So let's just see what's happening when I'm sending two messages and I'm signing them. So Alice is sending these two messages, M1 and M2. Now, what is the signature of Alice on M1? It's just M1 to the power of D. This is D of Alice. Okay. Modulo N. And this is also N of Alice. And when she signs M2, that's M2 to the power of D, modulo N. And again, D of Alice, N of Alice. But now Dave has seen the signatures on these two messages. He can take the two signatures and multiply them. Right. So Dave can compute M1 to the power of D, which he has seen, times M2 to the power of D, which he has also seen. But this is the same as M1, M2 to the power of D. So this is bad, because now it means that Dave could create Alice's signature on a new message, on the message M1, M2. Right? So you have to make sure that your messages cannot be combined together. So you have to have a protocol that says my message has this particular format. Okay. So you have to say something like this. You have to say, whenever I send a message, my message is always going to be a string that starts with some particular thing. So let's say I say the only valid messages that I, as Alice, would ever send you to Bob are messages of this form. It's like, I am Alice, and my message is blah, blah. Okay. So whenever I want to send a message, I write this string. Of course, I have to somehow translate it to a number, right? So that part is fine. You can just imagine that, I mean, you have a Unicode or you have ASCII, so you can translate each one of these letters to just a binary number. And then if you have a large number n, you can consider that your entire message is something much larger. But your message has a template. It's something like this. Why do I do this? So that if someone multiplies two messages, they get garbage. Okay. So what's going to happen here is I want to make sure basically whenever I have two messages, M1 and M2, that are valid messages, M1 times M2 is not a valid message. So that when Dave can compute M1 times M2, fine. I mean, you find a signature on M1 times M2, but that's garbage anyway. No one cares about it. Okay. There are other techniques for this as well. Take the cryptography course. There are things called hash functions up here. But Dave can compute a bunch of other things as well, right? So instead of multiplying, you can divide. Dividing is basically just taking the inverse of one of the numbers and multiplying it by the other. And then you will get the signature on M1 divided by M2. So you can do all sorts of tricks like this. You can combine the signatures, but as long as you have a good way of ensuring that these combinations of messages are not valid messages, you're fine. Okay. But now I have to say one more point. We talked about these different keys. So we said that Alice has a private key D of Alice and a public key E of Alice, and Bob also has a private key and a public key. But very importantly, you cannot use the same key for both sending messages with encryption and decryption and for signatures, right? Because let's go back here. Remember that signing is the same as decryption, right? So if you're using the same key, if someone sends you a message and you sign it, you're actually decrypting something for them. And you don't want that to happen. Right. So again, imagine something like this. Imagine that I'm using the same keys. So let's say Alice has a pair of keys that she uses for both message sending and for signatures. And Bob also has a pair of keys that is used for both. So now when Bob sends a message to Alice, Dave can intercept it. This is an encrypted message. So we want to make sure that Dave cannot decrypt it. But if Dave can somehow get Alice's signature on it, that signature is the same as the decryption. Right. Now, how can Dave get Alice's signature on it? Well, tons of different ways of doing these kinds of attacks. So imagine that I take the message, I somehow divide it in two parts, and I fool Alice to give me the signature on each of those two parts, and then I multiply them together. I get the signature on the message I was actually looking for, which is going to be the decryption of the message from Bob. So what you actually have to do is that each person should have two pairs of keys, right? So if this was not already complicated enough, I'm going to have this situation. So I have Alice on one side, and I have Bob on this side. Now, Alice is going to have keys that are used for sending messages and keys that are used for signatures. So she's going to have, let's say, EA1 and DA1. Or actually, let me just, I don't know what to call it. Let's call it EAM, the public key of Alice for sending messages, right? And she's going to also have DAM, which is the private key of Alice for receiving messages. And of course, there's also going to be an NAM, which is the modulus used when you're sending a message to Alice, right? And then she's also going to have a public key for signatures, a private key for signatures, and there's going to be a modulus for that. And Bob is also going to have all of these things. So I'm going to have the public key of Bob for sending messages. There is the modulus of Bob for sending messages. And I'm going to have the public key of Bob for signing, the modulus of Bob for signing, and of course, there are corresponding private keys. So the private key of Bob for sending messages and the private key of Bob for signing. Okay. So now, finally, when Alice wants to send a message to Bob, what should Alice do? Alice should encrypt the message so that only Bob can read it, but she has to also include her signature so that Bob can be sure that it came from Alice. Okay. So to send a message M, to send M from Alice to Bob, Alice should do this. Well, first, I'm going to sign my message. Okay. Now, again, when you take a cryptography course, you're going to see that you actually sign the hash of your message, but for now, it doesn't really matter. So step one is to compute some signature. Let's call it S. And this is going to be the signature of Alice. So this is the signature of Alice on my message M. But what key is Alice going to use to sign? This is like the private key of Alice for signatures. DAS. Right. And then the next step is that you just concatenate the messages together. So let's M prime be M concatenated with S. And here I'm just thinking of my messages as like sequences of zeros and ones, so I can just put them together. And imagine that I put a comma in between as well, so that we know which part is M, which part is S. Okay. So I have this M prime, and now I'm going to encrypt M prime and send that. So step 3 is that I say, let's call this M bar, is going to be the encryption of M prime. But which key am I going to use for the encryption here? I want to be sure that Bob can decrypt it later. So I'm going to use the public key of Bob for messaging to encrypt it. And finally, I send it to Bob. So for send M bar to Bob. Okay. Now Bob can basically do the opposite. So when Bob receives M bar, he's going to first decrypt it. Okay. So step 1 is I'm going to decrypt M bar. So that's going to give me M prime. So Bob is going to find M prime, which is the result of decrypting the message that he just got from Alice. But what key is he going to use to decrypt? His decryption key for messaging. Okay. Now I have this M bar, which remember has 2 parts, M and S. So I know what M and S is. So I know that M bar is M followed by S. So Bob knows both of them, both M and S. And now he has to check that the signature is correct. Okay. So step 3 is that he's going to do verifying that S is a correct signature on M. But what key is he going to use for verification? This is the public key of Alice for signatures. Right. Okay, and of course, you have the opposite when Bob is sending a message to Alice. In this case, as you see, I'm first signing. When Alice wants to send a message, I'm saying Alice should first sign the message and then encrypt the whole thing. I think this is a better practice, but you can also do it in the opposite direction, right? So you can first encrypt your message, and then you can sign the encrypted message and send those 2 things. So you can send the encrypted message and a signature on the encrypted message, and then Bob will have to first verify the signature, which tells him that this encrypted message really comes from Alice, and then he's going to decrypt it and see what the original message was. You can combine them in any order, but the important thing is that you have to make sure you're using the correct keys, and you have to make sure that you're using the correct moduli, right? Because every pair of keys has its own modulus. So be careful about that. I'm not writing any of them here. I'm just writing encryption and decryption and so on. But you know that all of these things like signing, verification, encryption, decryption, it's just that you take whatever message you have, you raise it to the power of your key, and you take that modulo your n. So you have to always be careful to use the correct keys, but also the correct n. And the most common error I see, well, in the blockchain course, because in this course I cannot ask you to code, but the most common error I've seen in the blockchain course is that people mix up these n's. And when you do that, we will just get garbage. Like nothing will work.